Yeah, hello. Uh, Today we'll be checking out this paper. Uh, so this is the flexibility trap, rethinking the value of arbitrary order in diffusion language models. I'll be walking you through this paper and based on my understanding, like coming from the engineering background, how I to understand this research paper, I had to understand go back to the basic and understand some of the research things before I deep dive into the paper. So I will do it the same way how it helped me to understand the paper. So it's mainly for engineers who want to un- go through this research paper, not for the researchers. Okay, let's start. So here, what's the problem this paper trying to solve? So, we have the general LLM models, which are like the GPT, Claude, which predicts from left to right. Basically, if you know the architecture, like everything on the right side will be masked after the current one, so it will always predict the next word. That's how left to right will be going in. So that's how the model predicts iteratively. So that's the basic LLM model. So, but we have diffusion language model, which uh, predicts which predicts basically words at different parts of the sentence, not just from left to right. At the same time, in the same iteration, it might uh, predict the word at third position, fifth position, 10th position, whichever it feels more probable, the easy ones. So the next iteration it would go for the bit harder ones. So that's how diffusion language model works. If you think about this, with this approach, it will be quite fast in terms of runtime and things. That's why people go for diffusion language model. Like when you think about diffusion, it's you will be thinking about the image models, right? Where we add noise to the pixels and then we do go through the training. Here, instead of adding noise to the image, here diffusion model for text is nothing but will be keep masking some of the text in a sentence, and then we start with masking one word at a time, and then we end up masking all the sentence, all the words in that sentence. So that's how we start with. Maybe I'll share the other screen. Yeah. So whatever I try to say, I'll put it in words. Yeah. So when the all the state are masked, that's called the absorbing state. So we start from the absorbing state where all the words are masked, and then we go through iterations where we keep unmasking the words at different arbitrarily across the sentence, not just from left and right. So yeah, so they basically use the absorbing state. So and then the process or the technique they are used is called Markov chain. So we corrupt all the uh, words in the sentence, everything. We basically here we call it tokens, right? So before going to LLM, we basically convert the words into tokens. So basically we mask everything in the all the tokens, and then we start from there. And then we do iterate both ways. Are also because we are going to do it not just from left to right, right, arbitrarily across any part of the sentence. So we do it. We unmask the ones which are easier, having high probability, and then we are going to the next one. So it's a bidirectional, and then it goes on a iteration looping. So in each loop, not just one word will be replaced, a couple of words will be replaced in single loop. So yeah, this was I was saying. It will predict the high signal words. So that's how. the diffusion LLMs, which is DLLMs, work. The so when DLLMs does this, it has some issues with the words, with the structured words. The words like if, however, therefore, because for all the objective words, it will easily figure out, and then they fill those up first, and then only the gaps or tokens, which is for the if, therefore, these kinds of conjunction or structured words will be mastered at this point of time. And when it tries to predict that word, most of the time it goes wrong, and then the accuracy drops, and the LLM hallucinates as well when we tries multiple times against the entropy laws. So that's the one of the issue with the diffusion model. Though that it's quite fancy and quite do the predict the words in quicker way, like compared to the normal left to right ones, but it has these issues. So this problem tries to solve this issue. So for solving this issue, people basically take the pre-training model, which let's say here pre-trained model is DLLM model, right? And then we do the post-training, which can be a RL, reinforcement learning. So during reinforcement learning, people also do similar for diffusion model. They again do this diffusion model way of reinforcement. So they again do predict the word arbitrarily, and also using PPO technique, which is invented by OpenAI. But this paper tells about we can go for GRPO and the just GRPO with Z score function. Also, like we are going to do it left to right, like a general LLM, sequential LLM model. And then if we do that, if we during RL, if we predict from left to right, though it's a DLLM model, we can see that accuracy across different problems, across different data sets, the accuracy is basically higher than the uh, other models, other way of RL. So that's what this paper is suggesting, and it's trying to prove it. So this is the one of the top award winners of from ICML. This paper for this year. So this problem, the solution is quite simple. And this basically makes uh, better problem solving. It solves the problem basically. So to understand this, there are a few terminologies we need to understand. Let's start with uh, okay. So these are like not related to the paper. These are very basic things like how engineer talk versus how a researcher talk, right? And then versus how a institutional, let's say professor or like who are studying in the institutions, they talk to this. Basically, I'm trying to map the language, each other's language. So when they say in their jargons, we understand what they're trying to say. So basically, like LLM model or transformers are nothing but we predict and then we calculate the loss and then we calculate gradients and then we go back and update the weights, right? So we when we say calculating the loss or error, so for that is called information theory in the formal mathematical or theoretical institutions. So whenever they say information theory, which includes KL divergence, to reduce the overfitting, like basically like not to here overfitting. By overfitting, I mean not to update the weights too much that the vector, the new weight got too much deviant from the original weight, and then cross entropy for error. And then the research, let's say if there is a researcher, they'll be calling this as an objective function. Why they are calling it as objective function? Because this is the core of the particular uh, model, right? So they call whatever the core of the particular model, which determines how the model works. Let's say for an engineer, if something fails, it will be the core logic, right? We'll be going to that core logic and then we'll be checking that. Similarly, for researcher or any model, if it fails, they go to that objective function and check if there is any issue with that uh, formula or the derivation. So that's why they call it objective function. And then the next step is once we calculate the loss, we go back and update the weights. Uh, so we do chain rule here because we have multiple layers. So we basically calculate that weight across multiple layers, like layer 1, layer 2, layer 3. So there is a particular derivation for that also. So that in formal theory they call it multivariable calculus because it has multiple variables, right? For each layer we have a d layer 1, d layer 2 divided by d layer weight, something like that. So that's why it's a derivative multivariable calculus. For in the research terminology, they call it back propagation or gradients autograd. So we need to call it back propagation or gradients autograd. And then we use Z-score to update reasoning rules. So in during the RL, uh, how we like during our just GRBO technique, like later you will understand this more depth when we go through the flow. For now, just understand this. We use Z score basically to figure out the score of each of the predictions with the left to right model, and then yeah, that's what we do. We basically try to run 5 or 6 groups or like 8 groups, a number of groups of predictions, and then we take the average. So instead of average, we basically yeah we calculate the mean and standard deviation, and then we use it in Z score. Z score usually it will be like actual value minus mean divided by standard deviation. So yeah, that's the Z score formula. So engineer, we call it the raw term using just code to update the weight. But in formal theory, they call it the rewards, reinforcement learning rewards. In the research terminology, they call it advantage calculation or policy optimization. So here, why they call it policy? In researchers, they call what are the model predictions as policy. They won't call it predictions; they call it policy. So here we are updating the policy. So like policy is nothing but weights basically. Here predictions are nothing but weight, right? So we are basically updating the weight. So weights those are nothing but policy. So policy optimization or advantage calculation. Just understand these things. So let's say when you are in a call with researchers, how you need to talk to him, they need to understand them as well in their own language. For that, so they call for the base model objective function. So there is a objective function for everything, right? Base model for loss, and then for RL. So for everything there will be a core function which determines. So that's the objective function. You need to understand that. Whenever they say it's an objective function, it's the core logic. It can be entropy loss, or it can be the RL calculation. So what are the core derivation, the information theory. Discussing oral just GRPO during objective function maximization GRPO advantage score, but includes a KL penalty prevent control. So here you need to again understand when they say objective function for RL, it's the for the across the group we calculate the uh, score uh, by using Z score. Uh, And then we also do KL penalty, KL divergence here because we don't want to make sure weight is updated too much from the original model. So we do KL penalty. So that's what they're saying. So whenever we need to ask a small question to them, we can talk to them in their own language. What exactly are we optimizing objective function, or are we just maximizing the reward? Is there a penalty term in there? So these are some of the basic things we need to know. Let's go to the actual paper. Like not the actual paper, actual core things before we dive into the paper. So once you understand these things, like let's say for an engineer, then it will be then when we go to the paper, it will look familiar. If not, if you directly go to the paper, it will look very alien to the engineers because we are not used to it. Maybe once we finish like 10 to 20 papers, then we might feel familiar. Yeah, but if it's the first paper, then this is the way for first few papers until we got into their shoes. So uh, for like this is just at the general LLM level. Whenever we say objective function, in information theory or the loss calculation, entropy loss, language models usually, right, it outputs probabilities. Like at the end of the iteration, what it calculates is for the next word, let's say we are in fourth word, it's pretty in fifth word. For all the other words in the sentence, it will figure out, it will tell. So this during training, right? So basically, for all the other words in the sentence, it will be basically not just sentence, like during all the words. It will be checking. It will be telling how much probability this word will come. This word will come. So it will be like a probability distribution value. So in this, it will we will be basically taking highest probability. Uh, so basically, we'll be weight. If you look at the LLM flow, right, we will be multiplying this weight with the actual value vector for that word. Basically, we multiply everything 0.01 into that word, and then we sum everything to that actual weight. So actual weight will get updated a bit towards therefore more and lesser to apple or car. So here we also KL divergence mathematical distance between. So we do so we don't want to update the weight too much. So that's where we come up with KL divergence to make sure the uh, it's not updated too much. So this is the formula for KL divergence, where we are calculating KL divergence of P and Q. P is the probability distribution and Q is the actual value, I think. So we figure out, we make sure it's not going too far from the original one. So that's the thing here. And then the next step, right? Let's say once you calculate the loss, then we need to calculate the gradient. So on the once after the gradient, basically we go back and update the weights in the during the back propagation, right? So that's what we are doing. Uh, so here we basically calculate loss, and then we do apply chain rule basically to calculate the gradients because we have multiple layers, as I said before. We do calculus, multivariable calculus, because it's multiple layers. So we do calculate, we get the weight loss and weight. The once we have that, we'll be basically storing it to a variable for each word. What is the weight, each vector, and then during the next layer, we basically go and we do back propagation, and then we go for each layer. We have something. Then we go and keep updating the weights to all the layers. So that's what we do. So next, in the first phase, we just learnt about. So basically, to understand this research paper, there are four phases we need to learn. The one is the mathematical bedroom, where we cover the objective function and then how we calculate gradients and the back propagation at a high level, because these are like general LLM terms. So I don't want to go deep dive. And then now we are in the phase two out of four phase uh, require requisites. So in the phase two, we see demystifying reinforcement learning. So here we are saying why people like previously people are going with PPO for the reinforcement learning, but for PPO it will be like training another LLM model from scratch. It's like a critic model basically to calculate, right? So it will take lots of VRAM and lots of performance, lots of resources. So that's why we the PPO term has come up from OpenAI, but the Quant team, right? They come up with the GRPO. So GRPO is relatively faster and easier on resources. So what we do is we prompt the main model. We ask it to generate a group of answers, and then we take a literal average. and then we apply just score on that. So basically, that's what GRPO does. So instead of actual model, pre-trained model, uh, generating just one prediction, we ask it to generate like let's say 8 predictions. Here group equal to 6, right? So group can be 8 or any number. So we ask it to predict that many times, and then we take a average and standard deviation, and then the just score formula is actual reward minus standard mean minus standard deviation. So we do that. So that's how we, uh, yeah, we do reinforcement learning with GRPO with lesser resources, because here we don't need to train a critic model like in PPO. So yeah, so with that being said, how so so before going on to phase three, we also need to understand how diffusion model works. We already walked through how this works, right? Start with observing state, where everything is masked, and then we unmask one at a time, not one at a time, multiple tokens will be unmasked in a iteration, and then the harder ones, like structured ones, will be the last, and then that's where the issue is. It will hallucinate because it's hard. It will the error rate will increase. That's the issue with the DLLMs, right? Large language model. So that's what we are trying to solve. Just to give a background. So yeah, let's go on to phase three of four phase prerequisite. The third one is flexibility trap and just GRPO fix. So flexibility trap and the just GRPO fix. The mathematical bug flexibility trap. Because the DLLM can generate anywhere, it predicts easy payload objects. The mathematical bug flexibility trap. Because the yeah, so this is what I was saying. The why DLLM is not good, right? It it predicts the easier ones, the actual objects first, the payload, and the structured words are the ones which it's harder to guess. So it predicts at the last. Probability score will be high, so it won't be predicted in the earlier iterations. So it will come to the last. So that's where, like, when we try to predict this, the loss will go high, and then it will hallucinate, and the prediction won't be better. The solution that we are proposing is just GRPO. So that's how we will do a reinforcement learning from left to right, like the normal sequential LLM, and then we basically improve their performance. So that's what we are going to see now. So as I said, just GRPO forces the model to reason from left to right during RL. So during while doing that, we force the model to predict the words with the low probability scores, like if first, because we make sure we force the model to predict them before going on to the next one, though the probability score is higher. So by doing it, we are improving their weights. So what we do, we calculate the advantage scores. Basically, we do it across groups, right? There can be like GRPO is nothing but like 8 groups, let's say. For 8 groups, we calculate the uh, mean and predictions on their mean and standard deviation, and we apply the Z score. And then yeah, and then uh, to make sure it's not like weight is not updated too much, we are updating the KL divergence. So that's what we do here. The phase for the PyTorch reality. Yeah, so far, like during the general ML, we will be just using the libraries, just ML libraries, like the ones where we just do a dot fit, dot transform, all these things, right? Or if we use even in the for the LLM ones LLM models, if we use Hugging Face or other libraries, still it will take care of the things. But when for the researchers, they basically go and update the gradients sometimes themselves if it is too much. So for that, we need to have a better control, for which we need to use, for which we need to use, um, for which you need to use um, better. We need to use the PyTorch here. We need to write the PyTorch code to figure out, so we can fine tune the things better. So now we'll be going to the actual how the PyTorch code looks like, just the general ones. Uh, so for the normal pre-training, there will be only these many um, parameters we pass: batch size, then sequence length, vocabulary size. So these are the general parameters. But for GRPO, since we are going to ask the base model to predict for multiple times across multiple groups. So there will be a group size variable extra. So that's the only change with GRPO. So basically, what researchers do is, when they figure out Gauss entropy laws. So what happens when we just add this and then we try to do it in our PyTorch, then we get the out of memory error because suddenly it increased 8 times, right? Let's say group size 8. So you'll get out of memory error. So in that case, we need to tune it, fine tune it. So what researchers does is, they manipulate the tensors, which is nothing but the weights, and they try to detach into multiple scalar vectors, and then they do it in parallel or do it in multiple levels. So that's what they do here. So during the phase two, basically we were applying GRPO with just score, right? So that's what we are seeing. So there will be a method that gets the mean and then the standard deviation and then do the z score. So z score value is nothing but advantages. That's what we call it, advantages. So we calculate the advantages and then we'll be doing the KL divergence here. Yeah. So we to make sure we are not updating way too much, we also do KL penalty. So we pass the advantages, then current logs, ref logs. So we have the loss and then this is the formula for KL divergence. So we have the objective loss now. So yeah, that's how it goes. So first we calculate the advantage and then we apply the KL penalty. So the flow will be like during the post training, right? That we do. We generate G responses, the number of groups, and then we calculate advantages, and then we using Z score, and then we calculate the Z KL loss. We make sure we calculate total loss. Uh, and then for total loss we also apply KL divergence, and then we do whenever we do this dot backward, what it does is it computes the gradients across multiple layers, right? So this is a multi calculus. So this is what we do here. We have seen the formula for this before earlier. And then the optimizer step is actually where it goes back to each layer and updates the weight. So yeah, this basically updates the weight. So this is how your PyTorch code looks like, the step-by-step approach. Yeah, so now we have all the basics to basically go through the paper. We have all the prerequisites ticked. Let's directly go down to the paper. No more waiting. This is the one of the simplest, more theoretical paper. So it will be a good start for the engineers who want to read papers. Let's go back to the paper. Yeah, so this is the original paper they basically uh, developed. So the flexibility trap, rethinking the value of arbitrary order in diffusion language models. So basically here we are rethinking the order, right? So during the RL, we are forcing the model to predict left to right. So that's the title. So these are the metrics when they benchmarked it against different. So this GSM 8K, Math Find, Human Eval, MBP, these are all the different benchmark data set that they use. One is Human Eval data set, MBP is Python course. How good is it in generating Python course, math, GSM 8K. So what we are having seeing here is so blue is the arbitrary order. That means it generates randomly, right? First word, fifth word, and then at last comes the original model. So same way if we do it in the AR, which is our actual like the left to right order, so we can see the accuracy is better. Uh, so when the number of samples are high, the number of samples here is nothing but G. When the number of groups is higher, during just GRPO, the performance is increasing. Uh, yeah, we can see against all the data sets, the performance is better with AR with our just GRPO technique where we forcing from left to right. So, so let's go on to see this, what they're saying. So this is same thing which I said, right? With just GRPO, they're saying reasoning is better now. So it's getting validated across all the different types of data sets. So now diffusion large language will break the rigid left to right constraint of traditional LLMs in token emission arbitrary orders. Yeah, so they are again going to the same thing like what we discussed. So basically, diffusion large language models (DLLMs) basically they don't do left to right. They like a traditional LLMs. They just generate in arbitrary order. So it's flexible and it's quite fast as well. Uh, so, in theoretically, they should unlock superior reasoning potential, but for the general reasoning task like our mathematics coding, the arbitrary order, like the ones come in between, are very important. The low probability ones, like the structured ones, like if therefore. So because of that, the it's not performing well. So that's the actual uh, thing when it comes to the actual task with the DLLM models. Um, so that's why people want to apply RL, which is a post training, which we do for making sure the LLM model is having a good behavior and helps humans instead of just learning about words, which is during the pre training. Um, so So here we make the models. We apply. We are going to do RL reinforcement approaches for DLLMs. Uh, so the complexities are because multiple trajectories, right? Because it does across multiple different arbitrary predictions. Uh, but what the paper suggests is just instead of going arbitrary order, we simply force it to the particular left to right order by using the GRPO technique instead of. So our approach is just GRPO. That's a minimalistic. We are seeing about accuracy of 89.1% for the GSM 8K. So that's what we seen here. And then the flexibility trap. Central to the appeal of DLLs is that with some opposite of. So we have seen the this kind of DLLMs has good benefits across specific tasks like Sudoku or Zebra puzzles, where the order doesn't matter. But for the general task, still it doesn't it isn't doing good. So now people are trying different RL approaches on top of these DLLM models to make sure it's even better for mathematics and coding. So here they are challenging intuition. Uh, Instead of for the general reasoning task, arbitrary order generation may be in fact narrow rather than expand reasoning potential illicitly by RL. So they are just challenging that thing and then they are saying like how we are going to do it. So here we compare both the approaches. The blue is the arbitrary order, left is the AR, the strict left to right order, right, that we propose. So we do it across. So these are like different DLLM models. Like we have a LADA 1.5, Dream Instant, LADA Instruct. So these are different models. For all these models across different benchmark, industry benchmark data sets, we see everywhere, we see when we increase the group size, the just GSM with our left to right technique, just GRPO with our left to right technique is basically performing very well. So that's what we are seeing. Um, so that was the finding one. So with arbitrary order, basically they are saying the potential will be reasoning will be bad, but with when we do it left to right, the reasoning is better during RL. So we save best of both worlds. So the second finding is arbitrary order explores a subset of AR solution space. So what they are trying to say is one might hypothesize that arbitrary order explores a different solution space less efficiently. So for arbitrary order, they are in different space, right? Because they are printing at different places across the sentence. So how we are going to test this? We are going to set the k equal to 1024. Uh, while we when we done that, we figure out the reasoning traces generated by arbitrary order largely a strict subset of those generated by AR. So basically, what we figure out is whatever the arbitrary order generates, those are just a subset of what the actual order, what we do after RL, right? The left to right, it is just a subset of that. So basically, uh, if you see everywhere, it's just a subset of that, right? So we are already seeing the left to right AR order is better across all these benchmarks. So later mechanism. So yeah, so we are going to see why this theoretically superior solution space for DLLM collapse in practice. So DLLM is a big technique, big thing, but still in practice it's not doing well. And then here we are just seeing why it's not doing well. So in the left to right order, we let's say these are the more objective words, and the red ones are the structured words like if, therefore. When it comes to the structured words, the left and right, since it's going left to right, one word at a time, one token at a time, it's forced to predict this, then go next. But during the arbitrary order, in every iteration, it just takes the high probability, easier ones. So it skips the harder ones and moves back to the next one. So because of that, during next iteration or like further iteration, when it tries to predict this, the error rate goes high, entropy loss goes high, and it hallucinates. So that's the reason. So here we try to portray why it does this way. Um, yeah. So here we also see what are the words like for. So basically here we try to figure out these red words, right? What are the in practice? What are the words basically come out as these structured words for which the arbitrary order is not performing well. So most of the time these are the connector or transition words, but they hold a big meaning basically if they change it, right? So you can see for these word performances, just for this word, the orange is our left to right order, traditional one. So it performs very well, right? These are the some of the samples words that DLM suffer most while predicting this ones. So with just here pivot, we basically ground us with the simple technique, just calculating the just score advantages across multiple groups. Um, though current RL, they tried various methods. With this simple just GRPO, we are able to get the better performance. So that's what they are trying to say. So they propose just return to simplicity instead of going for complex ones. Pure auto order yields better reasoning. That's what they're saying. And then basically like this is how the formulation works, right? So to update the property of next word, everything is mastered first. So this is that in absorption state as per DLLMs. So then it tries to predict the next token to randomly, right? So this is how it will be, and then it applies softmax. So just to confirm, what are we tried now? The RL and AR, which is left to right. This is applied only during training, where we update the weights for the bit. But during inference, it's still practicing the actual base model, which is arbitrary function and arbitrary prediction. In parallel, it capability of predicting the words in parallel. So still that works in inference time. During training, we do the RL where we update the weights with left to right prediction. That's what we are saying here. And then this is the comparison. Previously, we've seen it in charts. This is in the tabular format. Um, so we also see whether training with the AR approach, which is left to right, just TRP approach, uh, has whether it impacts the model's performance during inference. So that's what we are saying. We are seeing here, but we you can see still for across all the data set, the performance is better in terms of accuracy compared to the general uh, arbitrary models, which is blue. So yeah, so we come to the conclusion. So what they are saying is you can read through that as well. I will share the link in the comments. The intuition appeal. So basically, they summarize the things here. You can read through it separately. That's pretty much. I think for engineers who think research papers are kind of early in technique, so this will give you a good start. So just don't stop from here and start taking up such papers. Start reading. Yeah, we can do it. Yeah, thanks everyone.